Section 10.4 notes, infinite geometric series. Let's begin this by opening up our notebooks and jotting this down as a title. Now, as we begin this section, let's analyze the words here. Infinite means that it continues forever. A geometric series, well, geometric is a list of numbers that has a common ratio between each number, between each pair of numbers. And a series is simply adding up all the numbers on that list. Now, I know what you're thinking. Well, if it's forever and you keep adding, then isn't the answer always going to be infinity? Well, for sure with arithmetic, that's the case, right? Arithmetic. Let's say I had a common difference of 2. So let's say our first term is 2 plus 4 plus 6 plus 8 plus 10 plus ... and it keeps going forever and ever and ever. What's your answer going to be? The answer will most definitely be infinity. And this is an arithmetic series, an infinite arithmetic series. So one thing that you could say right now is that any infinite arithmetic series will always approach infinity. It always will equal infinity, right? It'll never have an actual answer. It's undefined. It's infinity. Now, this is why they call it infinite geometric series, okay? A geometric series, there's two types of geometric series. And in order to begin this discussion, let's look at our book. And in our book, it has a definition. An infinite geometric series has an infinite number of terms. We already know that. A series that has a sum, what does that mean? A series that has a sum. If you add up a list of numbers and it has a sum, and we're talking about infinite series here, that's what we call a convergent series. Convergent series. So this is a vocab word we need to memorize. So if it actually has an answer, I know you guys are thinking, how is it going to have an answer if you continue to add and add and add forever? We'll get to that in a moment. But anyways, when it actually has an answer, that's a convergent series. Because the sum converges to a specific value, and again, we'll talk about that in a little bit. A series that does not have a sum, right, an infinite series that does not have an actual numeric answer, that's what we call a divergent series, right? Pretty cool, right? Yeah. So divergent series, that's what we call an actual series that does not have an answer. In other words, it goes on to infinity. That's what we call a divergent series. Divergent! So if we move on to the key concept down here, so you could really understand the difference between a convergent series and a divergent series. Okay, that's probably getting a little distracting. I'm sorry. Anyways, so yeah, convergent series, it converges to a certain value, okay? So here is a geometric series that actually converges to a certain value. You have 5 plus 2.5 plus 1.25. What's the common ratio here? Well, what's half of 5? It's 2.5. What's half of 2.5? What's half of $2.50? $1.25. So this is obviously the common ratio of 1/2, okay? And the way you're supposed to calculate it is do 2.5 divided by 5 on a calculator. And you'll see that the answer is 0.5, which is 1/2. Or 1.25 divided by 2.5, which is also 0.5, which is 1/2. So when you look at the common ratio on this geometric series, if that common ratio is less than 1, then it will converge to a certain value. It's kind of like an asymptote on a graph. And we remember exponential growth and decay functions. It's kind of like an exponential decay function. This one decays to the certain value 10 in this case, right? So again, just like decay functions in the past, the decay functions in the past had a base that was less than 1. That was a decay function. If the base was greater than 1 on an exponential function, then it was an exponential growth function. I hope you remember that. So the same exact thing is happening here. If your common ratio is less than 1, it's going to converge to a certain value, to the asymptote graphically. If your common ratio is greater than or equal to 1, then it's going to diverge. What does diverge mean? It's going to go away to infinity, right? Could go to positive infinity, negative infinity, kind of like an exponential growth function. And once again, back when we did exponential growth and decay functions, if the growth factor was less than 1, it was a decay, which means it would decay to a certain asymptote value. and if the base was greater than or equal to 1, well, actually not equal to, but if it was greater than 1, it would grow the exponential growth function. So it's very similar to that, very related to that. So now you know how to determine whether it's a convergent series or a... Okay, I'm sorry, I'll stop. All right, so example 1, determine whether each infinite geometric series is convergent or divergent. How are we going to know if it's convergent or divergent? Again, if your ratio, common ratio, is less than 1, it's going to converge to that asymptote value. If it's greater than or equal to 1, it's going to be like an exponential growth. It's going to grow away, so it's going to go to infinity. Okay? Simple as that. So let's look at this example. What is the common ratio here? Well, you just take this number and divide it by the previous number. Common ratio is 24 over 36. If you reduce by 12, it'll be 2 over 3. That's technically the decimal number 0.66, and it continues, right? So the question is this R, 2/3, greater than 1 or less than 1, right? Well, it's less than 1. That means that it's kind of like a decay function, which it's going to actually decay to a certain asymptote value. It converges to a certain value. It converges, not diverges. So the answer to A right here is convergent. Convergent. And that's exactly what they explain right here. They give you the R, which is 2/3. They use 36 over 54. I use 24 over 36. It doesn't matter. It's going to be common. And of course, your R is 2/3, which is clearly between -1 and +1, which means that it's convergent. It converges to the asymptote if we were thinking about a decay function. Now, if the R would have been greater, then it would have been divergent. Okay, let's take a look at one of those. On page 684, the very next page, the next example B, if we wanted to find the common ratio here, you do 18 over 12 or 12 over 18. As you can see, 12 over 18, if you actually do that on a calculator, it'll give you a value that's greater than 1. And they tell you since 1.5 is greater than 1, then the series is divergent. Divergent. So that was the first skill that you need to acquire on this section to be able to tell whether it's convergent or divergent. The second skill that you need to acquire is this key concept right here in our books. It says the sum S of an infinite geometric series with the common ratio being less than 1, which would make it divergent, is given by this formula. S equals your first term divided by 1 minus that common ratio on your series. It says if the absolute value of R is greater than or equal to 1, then the series has no sum. Why? Because if R is greater than or equal to 1, then it becomes divergent, which goes to infinity. Okay, it has no sum, it would be infinity. So let's go back to our notes and jot down the key concept, sum of an infinite geometric series, the formula for the sum of an infinite geometric series, and let's copy this down. There it is. Now let's take a look at example 2 from the book. Let's actually copy it down in our notebooks. So it says right here, find the sum of each infinite series if it exists, because why? It might be infinity, right? It says determine whether each infinite geometric series is convergent or divergent. So we have this series, and they want us to first say if it's convergent or divergent, because that's how you'll know if your answer is infinity or if it's an actual answer where we could actually use this formula to find that answer. Okay, so if it's convergent, then yes, we're going to use the formula to find the actual answer of the summation of the infinite geometric series. If it's divergent, we could just say that there is no sum because it's infinity. It continues on forever. All right, so let's find out if it's convergent or divergent. How do we do that? By finding the common ratio. If the common ratio is greater than 1, then it's divergent. If it's less than 1, then it's convergent. Let's take the fraction 6/15 and divide it by the previous term 2/3. This is easy to do. The first fraction does not change. You change the division to multiplication, and this 2/3, you flip it and it becomes 3/2. And then after that, you actually multiply it through and reduce. So you could multiply then reduce, or you could start canceling things out right now as we speak. So let's cancel the 2 on the bottom and the 6 up on top. 6 divided by 2 is 3, and that would be, of course, up on top. The 3 and the 15, they both could be divided by 3. 3 divided by 3 is 1. 15 divided by 3 is 5. And there is your common ratio, right, which is 3/5. The common ratio is 3/5. So this common ratio is obviously less than 1, right, which means that is it what? Convergent or divergent? It is convergent. If it's less than 1, it's like a decay function that decays to a certain asymptote, right? Same thing here. If your common ratio is less than 1, it'll decay to that certain value, which means that it is convergent. So let's write that down. Now that we know that it is convergent, that the values approach a certain asymptote value, right? We know that we could actually add up these infinite numbers that continue to be multiplied by 3/5, and we will, even though it goes on forever, it approaches a certain value, which means we're going to be able to actually add these up and get an actual answer. How? By using this formula over here, okay? So the formula says that the summation will equal your first term, which is 2/3, divided by 1 minus r, and we said that the r was 3/5. Okay, so what do we have here? We have 2/3 up on top, divided by, and let's find the answer to this so we could write it right here. So what is 1 take away 3/5? Well, in order for us to add or subtract fractions, we need a common denominator. Now, you might be thinking, well, wait, 1 is not a fraction. Yeah, it is. You could rewrite it as 5/5. So you really have 5/5 take away 3/5. So let's scratch out the 1 since you already rewrote the 1 as 5/5. So you have 5/5 take away 3/5, and now that you have a common denominator, you could actually do 5 take away 3, which will give you 2/5. So what we really have here is 2/3 divided by 2/5. So let's put the 2/5 right here. And of course, when we are dividing by a fraction, we really multiply by the reciprocal. And that first fraction always stays the same. So we could multiply top with the top, bottom with the bottom, and then reduce, or you could reduce first and then multiply. I'm going to reduce first because the 2's cancel. And what do we have left? We have a 5 left up on top and a 3 left on the bottom. So believe it or not, this is my answer, 5/3. You could also rewrite it, that's an improper fraction, you could rewrite it as 1 2/3. So what does that mean? This summation formula tells us that if I were to take 2/3 and then add it to 6/15, and then add it to 18/75, and then add it to whatever 18/75 times 3/5 is, that'd be your next term. And then if you kept going and going and going and going, your answer would get to this, 1 2/3. So this section of our book on 10.4 gave us 4 examples. And I don't know if you've noticed this, but whenever I assign book work, right next to the set of problems, it says example 1. Right next to the set of problems, it says example 2. So it gives you reference. So if you're stuck on one of these, you could go back to example 1, see how they worked it out, and it's going to be worked out exactly the same, right? That's what's pretty cool about textbooks. Anyway, our homework for the next 2 days, all right? Not for today, all right? Because we've only covered 2 examples, example 1 and example 2. On the next video tomorrow, I'll be doing examples 3 and 4. Then we will be able to complete the whole entire assignment. So right now we're going to focus in on the first half of the assignment. And the actual assignment is 10.4, page 686, 687, numbers 1 through 37 odd. So I am going to do a couple of these, and you're going to be able to do a couple more. And we're going to do about half of them today, and then the other half, after covering examples 3 and 4, you'll be able to do the second half of this assignment. So once again, jot this assignment down, but remember it's over 2 days, because 1 through 37 odd, that's a lot of questions for 1 day. And we're not even able to do it yet because we only have half of the knowledge that we need. Another detail about the book assignment is they give you a check for your understanding. So they go through pretty much a small version of your entire homework, right? They're doing these first 4 questions on example 1. the next 4 or 5 questions on example 2, and so on and so on. And then over here, again, example 1, example 2, and then the next page is examples 3 and 4. So today, I am going to work out examples 1 and 4, actually 1 and 3, since we're doing the odd ones. I'm doing them for you. So let's start with that. And all it's asking you to do on this first section is what we did on example 1. What was that? To determine whether each infinite geometric series is convergent or divergent. Yeah, okay. So anyhow, let's jot down number 1 in our notebooks, in our homework, and let's determine whether this is convergent or divergent, okay? So what is happening here? We have 6, we have -8, we have +4, we have minus ... and then it continues forever. So let's first find out that common ratio. That common ratio would be taking the +4 dividing by a -8. So if you have +4 divided by -8, that's really the fraction -1/2. Okay, and same thing over here. If you were to go -8 divided by +16, it would also give you -1/2. So the question is this common ratio, which is -1/2, is it greater than 1 or less? I shouldn't say greater than 1. Does it fall between -1 and +1, right? And the answer is yes, which means that this is a decay function, which means that it's convergent. It actually approaches an asymptote, all right? So number 1 is convergent. Why is number 1 convergent? Because it converges to a certain value. And why does it converge to that asymptote value? Why does it converge? Because R is between -1 and +1. I guess the correct mathematical notation for that would be -1 less than R less than +1. Okay, and that makes total sense because a decay function has a base that's between -1 and +1 as well. As long as it's a decimal or a fraction that's not outside of these boundaries, it's not greater than +1 or less than -1, then it's a decay function, right? But if it's greater than 1 or more negative than -1, then it becomes a growth function, which would mean it's divergent. So I hope we understand number 1. Let's do number 3. So let's find the common ratio here. Let's take the 0.7 and divide it by 0.5. 0.7 divided by 0.5. I'm going to jump to my calculator here. The answer is 1.4 on my calculator. Now let's say you didn't have a calculator. You could rewrite 0.7 as 7/10 divided by 0.5, which is 1/2. And you could write it horizontally, which would be 7/10 divided by 1/2, which would then become 7/10 times 2/1. Then you could cancel the 2. 2 divided by 2 is 1. 10 divided by 2 is 5. And you get 7/5. So it's up to you if you want to look at this as a decimal or as a fraction. Either way, your R is greater than 1, which makes it a divergent series. So, I hope we understand those first couple of questions. If we go back to the book, those were on example 1. So what I recommend right now is pausing this video and jumping to your actual assignment. I mean, this is our actual assignment, right? But you see down here it says example 1 also. Same exact instructions. So right now would be a good time to pause and jump and do 17, 19, and 21. It says determine whether each infinite geometric series is convergent or divergent. Just by finding the common ratio. If the common ratio is less than 1, it converges to an asymptote value. It converges, a convergent series. If it's greater than 1, if the common ratio is greater than 1, then it's a divergent series. If you don't want to pause it and do it, then you can do it later. Let's move on to this next part. So far we've done questions 1 and 3. Let's jump to 5 and 7. By the way, let's skip number 9. Let's not worry about that one for now. And on 5 and 7, they're asking us to find the sum, the actual answer, if you were to add up 440 plus 220 plus 110 plus 55 plus, and so on and so on. If you keep going forever because you continue to divide by 2 right here, you actually get an answer. How are we going to find that sum? Using the summation formula for a geometric, for an infinite geometric convergent series. So we already have this formula written down in our notebooks. I'm just going to rewrite it right here next to these questions. So let's take a look at number 5 right here. And let's find the sum. you're going to have the sum being your first term, which is 440, divided by 1 minus the common ratio. And of course, the common ratio will be 110 divided by 220, or 220 divided by 440, which we clearly know all reduces down to 1/2, all right? 1/2. So what is our summation really? It's really the 440 that's divided by 1 take away half, that's positive half, right? If you have one pizza and you take away half of it, you'll have half a pizza left. Anyhow, let's rewrite this horizontally instead of vertically. We'll have 440 divided by 1/2, and we're going to rewrite it as 440 times the reciprocal, which is 2 over 1, which is really just 440 times 2, which is 880. So there's my actual answer to this infinite addition problem. That's pretty hard to wrap your mind around when you're thinking about, I have a math problem, and I'm adding, and I'm adding, and I'm adding, and I keep adding forever. Keep adding forever. And your actual answer is 880, right? A lot of people will have a hard time grasping that, but since you guys have already done decay functions and you have seen graphs infinitely approach but never actually touch a certain value, this should make sense to you, okay? Number 7, all right, the summation will equal a sub 1. Our first term is 1/4, so I'm going to put 1/4, divided by 1 minus the common ratio, which I don't know yet. I'm going to do that by taking 3/8 and dividing by 1/4. 3/8 divided by 1/4 is the same thing as 3/8 times the reciprocal of 1/4, which is 4 over 1, which is just 4. And of course, I could multiply first and then reduce, or I could cancel the 4 and the 8 first and then multiply. Since I've been canceling always first, I'm just going to do it the other way to give you a little bit of variety. 3 times 4 is 12, 8 times 1 is 8, and 12 over 8, that could be reduced to 6/4, and then it could be reduced again to 3/2. Or you could just look at 12/8 and reduce both numbers by 4. 12 divided by 4 is 3. 8 divided by 4 is 2. So we really have 3/2 being the common ratio here. So we have 3/2 being the R. All right, so what is 3/2 really? You might want to rewrite that as 1.5 or 1.5. But anyway, what if you had 1 take away 1.5? Think about that. You have $1, take away $1.50, where you're going to still have a negative 50 cents. So you're going to have a negative half left over. So this summation is really 1/4 divided by 1/2. Now, let's rewrite this instead of vertically, horizontally. So that's 1/4. Whoops, I'm sorry about that. 1/4 divided by 1/2, which is really 1/4 times the reciprocal of half, which is 2 over 1, which is the same thing as 2. And you could multiply then reduce, or you could reduce first then multiply. 2 divided by 2 is 1. 4 divided by 2 is 2. So our answer is 1/2. So our actual answer to number 7, if you were to take 1/4, which is really like 0.25, plus 3/8, which is another decimal number, plus 9/16, which is an even smaller decimal number, plus another smaller decimal number, plus a smaller decimal number, forever, if you keep adding forever, and you add up all those infinite numbers on your geometric series, your answer will be 1/2. If you do it on a calculator, if you go 0.25 plus whatever this decimal is, plus whatever this decimal is, and you hit equal, you will see that the decimal number is getting closer and closer to 0.5, right? So the summation here is 1/2. Ladies and gentlemen, I've done the beginning part of your homework. I recommend, since we just did examples 1 and 2 right here, you guys do examples 1 and 2 right here, and we're doing the odd ones only. So do these 6 questions for homework, okay? And of course, tomorrow we'll do video 2, which covers examples 3 and 4 from our notes in our book, and then we'll be able to do the second half of the homework.